Hello. This video is about math and arithmetic. Nothing more, nothing less. Everything I'm going to present can easily be verified by simple calculations. While this video is for everyone, specifically it's for skeptics. I want the skeptics to take a serious look. Stay skeptical and keep asking questions. To me, this is not about pi being irrational or rational, or the square root of 2 being irrational or rational. I understand those proofs answer the questions that you were asking. To those questions, the results are absolutely correct. What I'm suggesting is that there are new questions that we can ask that may give us completely different answers that might surprise us. I only ask that skeptics keep an open mind and watch this as a thought experiment. Try not to get hung up on semantics or terminology. Follow along this walkthrough and my logic and methods. Verify and look at the results. It is only in doing this the most informed conclusions can be made by anyone. Okay, so let's get started. So this is what we know to be pi, right? The diameter divided by the circumference of a circle equals pi. Or if you use some advanced formulas, you get this converging to pi approximation. Now there's lots of different formulas that have been developed over the years by various mathematicians. But this has been the basic premise, that a circle is a single object and that pi is derived from adding more points around, or basically segmenting a circle into more subsections, essentially, or slices. That's why it's called pi. So this is the way we've understood pi up to this point. Now I'm going to switch the problem up a little bit, and this is what I was trying to solve. So I wanted to be able to place 9 circles or more, any number of circles, into a formation of a circle in such a way that they kissed and that there was no gap. So in this case, we've got a radius R1, and we need to figure out what the radius R2 should be in order for these circles to be placed in a circular formation without any gap in between. So that's what this slide describes. That's the problem I was trying to solve. Okay, so let's talk about the variable setup. I've ranked these according to logic, so the easiest ones to explain are at the top, and the hardest ones to explain are at the bottom, and we're just going to work our way through them. So we start with R1, which is the radius of an orbiting circle, number of positions in the circle, which is the number of circles we're placing in formation, the number of radian points, the number of points in a triangle, and then the degrees in a circle, 360. That's all good. Then I have a variable called t, which is for a period. I selected the number 28 because we see the number 27 and 28 a lot in the natural world when it comes to periods, like the moon or the tides. And then I have a golden angle reference, as I call it, which is the kind of the opposite of the golden angle. And this, in my opinion, would give you sort of a balance in orbit, almost like the golden ratio gives you the balance on a fractal. And then we have the synergy whole number constant, which in this particular context, in this equation, acts as a scalar and is going to give us a gradient. But I'll explain that when it becomes contextually relevant. I also have what I label synergy base and synergy limit. Now these two are the hardest of all numbers to explain. And I'm going to dedicate a certain segment of this video talking about these numbers, how I got there, and what properties they have. Okay, now it gets interesting. So these I call OctoQuadrian numbers. Now they may have been discovered already, I don't know. If there's another description for them, please let me know. Otherwise, I'm just going to explain how I discovered them, and we'll just go from there. Okay? So I started with 0.626. And I found that when you multiplied it by 216 or some other numbers, that it would actually return back in exact form the decimal of the number that you multiplied it by. From there, I kind of just playing with the number, I decided to feed it back into itself. And then I got another decimal that was 876. I kept playing this game, and it led me through a couple different numbers that had the same behavior. And they would give me these 87 number sequences. And there was 3 of them. The pattern breaks at 376, and it no longer works as far as it leading to the next. As you can see here, 626 leads to 876, 876 leads to 376, and 376 just returns itself. Then the pattern breaks. Looking deeper, once you get there, you find that these 3, the 376, the 626, and the 876, all have a gap of 250. You also realize that they're 1 plus in fraction form or in decimal form. They're plus 1 of a 3/8, 5/8, and 7/8. So I decided to subtract 250 from the 376, which gave me 126, and try that number as well. And sure enough, it worked. It gave me the exact decimal and the exact length. And again, there was 87 numbers in the sequence. Now, each of these numbers have 87 numbers except for the fourth, which has 90. There's 3 extra. And I haven't been able to explain that yet. I'm still researching this. But delving deeper into what these numbers do, they seem to have this really kind of odd 1/8, 1/4 behavior. And you also notice some things like this, where 0.126 multiplied by 5 cubed gives you 3.15. Okay, there's 4 octoquadrians. If you add up all the numbers in the sequences, you get 351 total numbers that work. That's the same digits as 3.15. And then on top of that, you have the polar opposite number, which is 648. And that's actually 4 times 162, which is what I call the synergy constant. So there's something really bizarre going on here. Again, I don't know if these numbers specifically have been discovered already, if they've got a label. If they are, please let me know. I'm definitely curious about finding out more information about these numbers as it pertains to what I'm doing. You also notice when you play around with these octoquadrian numbers, specifically 126, which is the first one, and also one that doesn't fit the pattern as far as one leading to the next, you find that it calculates out to a number very close to what we know as the radian constant. Now, this involves the first octoquadrian number with the number 2, which I think represents 2 points, or 2 positions, and then the synergy constant in decimal form. And this gives you a calculation that is awfully close to, in fact, nearly 1 off of what we know to be the radian constant. Now, in this particular case, and going with the theory that I have, which you'll be presenting here in a minute, I'm going to set this as a radian base constant. We're going to call this a base constant. So this is the base size of a radian. And what I mean by that is, when you look at a radian, you know, all the line segments are all equal. And when you bring the radian in, and it curves, it's that curve that's taking up the length of that radian. And what we need to figure out is what the radian potential is, in a matter of speaking, and how pi actually works in this slice, like how these radians work and how pi works. So I want to figure out what the motion is. So I call this a radian-based flux constant. Now, this flux constant is, you can think of it as a tax. So it's a tax based on the size of the circle. And obviously, the bigger the circle, the higher the tax. Okay. Now, this itself is more of a mill rate. This is the actual tax value. So we're going to apply this to the circle radius and the rest of the operations. So we have a radian flux and a radian flux ratio, and then finally the radian. Okay, and this is exactly what I was trying to explain. So when the radian comes in and connects itself to form that circle, basically we have this leftover piece of where the radian could have been had it not curved. Okay, and you can call that some sort of potential. And that number is extraordinarily close to R. So my theory is that as you add more circles to this formation, this X is going to get closer and closer to the value of R1, making the line seem more and more straight. That's kind of the premise of everything that I'm suggesting here. Now, it's an interesting coincidence that the actual angle that you would bring the radian 3 down to would be 250.333 on the opposite side. That's an octoquadrian angle, seemingly. And I've labeled it as such because I don't know if it's a direct connection, but it seems plausible based on how I got here. It should also be noted that the radian that comes back is almost exact, if not exact. How did we even get here? If we go back to the flux space constant in this equation, you know, there's a lot of structure that makes logical sense to how this is formed and the way that it affects and influences the overall equation. How do we get the exact radian? Which also gives us a very accurate value or approximation of pi. It just naturally falls out of the equation. So before I talk more about this SciPi and other things that we've found, I'm going to go ahead and solve the original problem, and then we'll double back on SciPi and the other discoveries. So the original problem is that we have to create a formation of circles with no gap. These variables kind of handle that aspect of the overall equation. I have what I call a gap flux, which I believe controls the space in between the circles, and then distance apart, which I think also influences that. Obviously, we have pi subtract y, so we have pi subtract we have the ratio of the circle subtracting the space that we need to remove from the gap. And then we have position ratio, which only influences the radian in the whole equation if and only if the number of positions is different than the radius of the circle. So in this particular case, we have a radius 1 of 9 and a position of 9. D is going to equal 1. But in all other cases where where the numerator is different than the denominator, you're going to have a different value for D. And then we get into these orbit types. So I call them orbit types because initially I had planned on just having the expanded orbit type. The compressed orbit type kind of just fell out, just like pi. So I found that if I divide the radius by the flux, the gap flux, that gets created by subtracting the gap flux from pi, that I get my expanded orbit perfectly. And then I found if I divide it by the number of positions, that I get this compressed orbit, right? So I called this orbit, and I have an orbit 1 and orbit 2 to express both expanded and compressed orbits. So now we're ready to solve the original problem. And we basically just multiply the orbit type by the radius 1 by the ratio of the radius to the number of positions. And that'll give us the exact radius for R2 of what we need to make a formation of circles with radius 9 with no gaps in between. So now that we've solved the problem, what the heck is going on? Why does it work so well? Why does pi show up to such a degree of accuracy? How is this all pieced together? Well, if we look at the radiant flux-based constant, which if you remember was the original size of a radian potential, basically, before it's brought in and adjusted to that curve. And SW, I said, was the synergy whole number constant and acted as a gradient. And this is what I mean by that. So the synergy constant is any permutation of 162. So that can be 126, 162, 216, 261, 612, and 621. Now I have lots of other information on why this number is the synergy constant, and I'll leave that for you to explore in other articles that I've written or videos that might be coming out. But for now, just look at this and look at the approximations toward pi. Right? We have 162, which comes in at the closest from everything that I've been able to tell. From there on, it either converges or diverges. And we have the full psi pi gradient, where I basically counted from 1,000 down to 1, which is oddly close to 22 divided by 7. And we get this whole gradient of pi. I just find that very fascinating, and I haven't seen anything in any lecture or class or document that explains pi to this degree of logic and accuracy. There's a lot of formulas and a lot of equations, and we all know that pi is definitely the ratio of the circumference to the diameter. But beyond that, there's been really no logic as to what's going on. So what else can we do with this information? How else can we test and prove what we're seeing is real? Well, we can start applying it to some of the equations that we know science is built on. In this particular case, this is the three-body problem. I found an open source simulation, and I merely substituted a static version of SciPy into the code. And basically what happened was the origin of the Kepler system is more centered when using SciPy versus pi. And I've been able to understand and see why. And what's going on is something that I call drift. Okay? So what is this drift and how can we visualize it? If we compare three different versions of pi throughout history, so we've got the synergy sequence theory, which is SciPy, we've got the JavaScript model, which is math.py, and then we've got Archimedes in 250 BC. Now you can see a distinct behavioral difference between at least two of the three, right? Two are static, they don't seem to move. This third, the Archimedes, seems to have this kind of a spin. And what I've been able to see is that different versions of pi throughout history have different drifts to their orbit. And that drift can either go clockwise or counterclockwise, depending on the approximation. But here you have synergy sequence theory, or SciPy, actually holding its own and performing exactly the same as the math.py of JavaScript. And there's another interesting property which I'm not displaying here, and I can prove, and that is that SciPy, the first position starts at exactly 0, whereas the first position on math.py is a negative number. And from a programming perspective, that's pretty satisfying. It would seem to me, logically speaking, that what's happening with this calculation of pi that's current is that it's kind of overcorrecting a little bit. And that's why we're seeing that negative number on the first placement. So what does this all mean, and where do we go from here? Well, there's so many equations that involve pi. I didn't want to just try to replace pi without having some sort of mechanism to handle that transition. That's why we called it SciPy. And we need people to try SciPy in their equations, try the method, just experiment with it and see what we can find and see if it produces interesting results. If it fixes problems, if it creates problems, there's so many questions that this whole thing creates. And it also, I think in some respects, forces us to take a look at how we solve problems and what constitutes, a hard problem versus an easy problem. Is P equal to NP? These are the types of things that I think this opens the door to. And regardless of whether or not this is right or wrong, I think it's striking. And I think there's definitely some things that we can look at and learn about pi and the nature of pi from this. And with that, I will leave it, and I'll thank you for your time and hopefully your skepticism. I hope that you think about this and go through the steps, watch it a few times if you need to, play with it yourself, test the equations, and try SciPy.